Let's continue with analyzing this form alpha in various different dimensions. We figured out it's a closed form, and we want to show that it's not exact as a form on Rn minus the origin. We did 1 and 2, n equals 1 and n equals 2. Now, let's do n equals 3. This is a good time to pause the video and try to calculate alpha explicitly in 3 dimensions and then calculate its integral. And now I went ahead and pre-did this one because it would be a little bit slow to do by hand, to do it live. Let's separate out a couple things here first. Oops, I don't really mean to do that. So here's the integral over S2 of the alpha in 3 dimensions. And remember what the definition of alpha was. It's a factor, and we'll talk about why you have this 1 over r cubed some more. And then the interior product with the radial vector field, which I broke out into components of dv, the volume form. Well, so that's going to give you x1 times the dv without the dx1, dv without the dx2. And if you do cyclic order, as usual in 3 dimensions, if you put things in cyclic order, you can write things with a plus sign consistently. Okay, so we've got this 2 form, and now remember it's a little tricky to write 2 forms in 3 dimensions or draw them, but oh, that's not a good one. Let's just do black, maybe that's going to be better. Okay, and that's going to be something that you want to think of as a flux. An n-1 form always represents a flux, or that's one way to think about it. And we're going to be integrating it over a sphere anyway in a minute. And we know that we can draw that as kinds of tubes, kind of a honeycomb or a cardboard crate kind of tube structure. And we've seen this before. It's something that where the flux is kind of out of these radially pointing tubes going out like this. If we actually went ahead and converted it back to a vector field, it really is, of course, a radially pointing vector field, scaled appropriately, which we'll see why the scaling in a little bit. Okay, so the integral of that should be calculating the flux of this highly symmetrical vector field through the sphere, and that should give us a fairly simple answer, and of course it will. So how do we do that? Well, first of all, we're going to take this vector field, take this 2 form, and we're going to pull it back by the parameterization. Oh, and I forgot to write that. So what I did as a separate calculation here, mainly because it wouldn't fit nicely on the screen otherwise, is let's call the parameterization phi, and we're really calculating the phi star. So the usual parameterization of the sphere is x1 is sine phi cosine theta, x2 is sine phi sine theta, and x3 is cosine phi. I'm using the mathematician's convention, or one version of the mathematician's convention, where phi is the polar angle and theta is the azimuthal angle that goes around, sort of around the equator. Okay, so we're really, phi star, remember, it's a very simple thing. You just plug in everywhere you see the x variables, whether it's inside a d or a wedge or not, you just plug in its expression in terms of the functions. That's the fancy way to say that is phi star acts on functions by just composition. And so we just change these. And then what we're going to be doing is this is going to replicate a calculation that you've hopefully seen before with like cross products and things like that, changing variables. But it's really nice how you don't have to know anything except this thing of just take the expression, put in the new functions in terms of the new variables, and then let the magic of the wedge product work. And it's going to take a couple steps, but it's going to be fine. So we plug in our sine phis and sine thetas and cosine thetas and everything into this expression. And then we just have to say, oh, d of a function. Oh, I know how to do that. That's, for example, here, you're going to take the derivative with respect to phi and put it in front of d phi. Derivative with respect to theta changes that into a cosine theta in front of d theta. Here, the derivative with respect to theta dies, so we only end up getting a d phi. We could put a plus 0 d theta, but it would be kind of silly. And then we do that for the second line as well. Here, this is fairly simple because this was just a function of phi. This guy is very similar to this, but with a little bit of a sign change, and the sines and cosines switched. And then down here, d sine phi cosine theta, that's exactly the same thing once again, as this one, rather. And then sine phi sine theta, that's the same thing. So we just copy it down here. Let me actually expand this out so we can see it all. Okay. So now you can either think of it as an amazing miracle or something that absolutely has to happen by the symmetry. A lot of cosine squared and sine squared happens. One thing that happens is d phi wedge d phi is 0, and d theta wedge d theta, for example, is 0. So a fair amount of the terms die. And then so we're going to get, and I chose to write everything with a d phi wedge d theta because that's how the sign worked out best. So I'm going to put everything in front of a d phi wedge d theta. So here I've got a minus, and this would give me a d theta wedge d phi, so I can cancel the minus by switching the order. And I get a sine phi, and it turns out that's an overall factor. That shouldn't be surprising if you've seen other versions of this calculation. And then a cosine theta squared and a sine squared, and that's this. Then here, d phi wedge d theta. Now it's two minuses, so, and there's no switch, so it works out positive again. Sine phi is an overall factor, sine theta, sine phi, so it's sine squared theta. Here, I get two terms. The d phi wedge d phi dies, the d theta wedge d theta dies, but I get two other terms, and if you look at it carefully, you might want to pause the video, you get cosine squared phi, cosine squared theta, and cosine squared phi, sine squared theta. Okay, so if you look at this, this is an overall factor of sine squared phi times, hey, cosine squared theta plus sine squared theta. Boom. This is an overall factor of cosine squared phi times, hey, cosine squared theta, sine squared theta. That's 1. And then it collapses to sine squared phi plus cosine squared phi. And so the whole thing is just that overall factor of sine phi in the front. And so the integral is just, you just integrate this over the parameter space, 0 to 2 pi in theta, 0 to pi in phi, sine phi, and that's a very easy integral. Remember, it just amounts to deleting this guy and treating it as an ordinary double integral. I did play a little fast and loose with whether this works right with the orientation. We would have to be careful. We have to make sure that that this is really the right orientation of the two-sphere that we really wanted. Well, all we're really trying to figure out is that this is non-zero, and this is a good orientation to use because it gives us a positive number. So I'm not going to worry too much about that. Now, but look at this number it gives us, 4 pi. That's the surface area of the two-sphere. And what was the answer before? It was the length of the one sphere, the circle. And in the first case, in the n equals 1 case, it was kind of degenerate, but it was the number of points on the 0 sphere, which is just 2 points, equidistant from the origin. So this is a 0-dimensional volume calculation. This is a 1-dimensional volume calculation. This, more complicated guy, is a 2-dimensional volume calculation. So we can guess that this guy is just the n-1 dimensional volume. I could put volume in quotes, although it's really, we shouldn't have to. Multi-dimensional volume totally makes sense to us, of the unit sphere in Rn. Now, we don't happen to know those numbers maybe. In another assignment for my class, we actually did calculate those, but there's a little bit of work involved. But we can at least be sure it's not 0. Okay? So if we just kind of guess that this pattern continues, that makes sense. Now let me show you why it would make sense for this pattern to continue. Remember what we did. Let's go back to 2 dimensions because it's easier to draw the picture. We took the volume form, which I'm going to draw like sort of like this in a piece here. And then we took the interior product with the radial direction, okay? And then we integrated it over the circle. Okay. Well, let's see what that's doing. Remember the 2 form, the green part here, its job is supposed to be to eat 2 vectors. You can't really read that, can you? Sorry, eat 2 vectors and give the area of the corresponding parallelogram. So that's an area calculation. But I've already fed in 1 vector. And remember what this vector was. This was like 1 over r to the n times the radial vector. Well, remember, if this is at radius 1, this guy is going to be a unit vector. Okay. So I'm already taking a machine that's supposed to give area and feeding it in a unit vector. Well, what's it going to give me? It's going to give me a machine that's ready to take the length in the perpendicular direction. And so I'm doing that at all the points around here, around the unit circle. And so I'm going to get a 1 form whose job is exactly to give the length on the unit circle. Similarly, in 2 dimension, or on the 2 sphere inside 3 dimensions, picture's a little more Fancy. I'm not going to try and draw the 3 form. Just have to remember the 3 form is the ambient thing that's present in all space that's ready to calculate the volume. Now I take again a unit vector because the r is equal to 1, and I feed that in as one of the inputs to the 3 form. That leaves a 2 form whose job is to combine, let's see, it's supposed to take a little patch of the surface and give me a number that when basically multiplied by 1 gives me the volume. So it's one way to think about it is I'm kind of taking a shell by using this unit vector and doing the interior product. I'm basically saying I'm going to take a shell of unit length that's perpendicular, or unit thickness that's perpendicular to the 2 sphere, and I'm going to take the volume of that. Well, the volume is going to be the thickness times the area, and if the thickness has been chosen to be 1, I'm basically going to get the area of the 2 sphere. Okay, so there's a very simple reason, although it's a little hard to make that super rigorous and precise, but there's a simple reason why taking the volume form, taking the interior product with a perpendicular unit vector to the sphere gives me exactly alpha being the n-1 dimensional volume form on the sphere. Okay, so the punchline here, alpha is the n-1, I need a dash there, dimensional volume form on the n-1 dimensional sphere. And that's, so if you integrate it, you get the total volume, the total size of the sphere. Okay. Now, suppose you didn't really trust that too much, or suppose you wanted to really calculate it for general n, and we're not sure how to calculate the n-dimensional, or the volume of an n-1 sphere. We can actually use a simpler argument to show that the integral is not equal to 0. Remember what the symmetry is here. Regardless of what exactly we're calculating here, we're calculating the same thing on all of these patches, because the sphere is totally rotationally symmetrical, and alpha is totally rotationally symmetrical, because the volume form was symmetrical, and then I'm interior producting that with a radially symmetric vector field, something that only has to do with r and the radial direction. And so whatever the contribution from each little bit is going to be the same from all the bits, so they can't cancel out. So clearly we're not going to get just 0 everywhere from the contribution here. And the only way this integral could be 0 is if there were positives and negatives canceling out. And that's not going to happen because they're all the same. It's all symmetrical. Okay, so no cancellations due to radial or full rotational symmetry. In other words, symmetry in all directions. So a non-zero integral. Okay, so part C and D are basically trying to get us out of what would be an interesting digression, which would be calculating the volume of an n-1 dimensional sphere. And maybe I'll do a video of that. As I said, my class has done that, but it's a little bit involved and kind of takes us away from the basics of forms. Okay, so now this is what I alluded to before. How would we use Stokes' theorem and either part C or D, just the fact that the integral is non-zero, to show that alpha is not exact? Well, remember, if alpha equals d beta, then Stokes says the integral over the sphere of alpha is the same thing, but with the d beta. This should be hopefully easy and familiar by now. That's the integral over the boundary of the n-1 sphere of whatever that beta is, but that's 0 because this is a boundaryless object. It's a closed submanifold. In this case, for example, it's a closed surface. Okay, and that's a contradiction. We know that the integral is not 0. Okay, so we've got our example here of, if we go back to the definition of alpha, we've got our example on Rn minus the origin of a closed form that's not exact. Let's go back and review something in 2 dimensions that we've seen before. Wait, it's right here. Okay, let's look at this. In n equals 2, if n equals 2, I don't know if I've done these in the videos. My students definitely did this. If n equals 2, I'm going to look at theta equals inverse tan y over x. And there's a reason I'm calling that theta. That's the usual polar theta function. And the claim is that alpha is d theta, which should be kind of weird because I was just claiming it wasn't d of anything. Okay, and let's look at the calculation there. Well, let's do it here to make it pretty. And I'll talk about the picture. Actually, I'll write the picture here. That's why I have this. Theta, well, I'll do the picture in a minute. I don't want to give away the punchline. Let's just do the calculation for a minute. D of inverse tan y over x, just a little exercise in the chain rule and the quotient rule. So that's going to be partial with respect to x of that guy times dx. So let's just write that out. Partial x. Ooh, that's a funky thing. Of this expression times dx plus a very similar thing with a dy. Okay. And that's going to be, so inverse tan, you get 1 over 1 plus whatever that argument squared is, so that's y over x squared, times the chain rule, and d by dx, we're going to get a minus y over x squared, and then that's all times dx, plus, same thing to start with, because it's still the inverse tan, and now the derivative with respect to y, that's just 1 over x times dy. Okay. So let's just multiply through everything by an x over, well, multiply this by an x over x, so that we'll have a common denominator. And the nice thing is the x squared cancels the x squared on the bottom here. And so you get 1 over x squared plus y squared as your common denominator. Oh, that's r squared. That's cool. And then what's left over here is a minus y dx plus, and here it's an x dy. Okay. And that's exactly alpha in 2 dimensions. Okay. So why is this disturbing? It's because this isn't supposed to be exact. Well, let's look at, remember, if alpha is d theta, it's supposed to be the picture of alpha, the stacks picture is supposed to be just the level curves of this function. Well, the function is kind of funky. First of all, you can observe that the level curves come together, which they're not supposed to do at the origin. But that's okay. We already knew that this thing wasn't defined at the origin because r squared blows up there. No big deal. But the real interesting thing is, what are the values here? Theta equals 0, theta equals pi over 2, theta equals pi, theta equals 3 pi over 2. Oh, wait a minute. Theta equals 2 pi? Which is it? The point here is that it's not well defined as a single continuous function. So the first and best example of something that works locally but doesn't work globally. As you start here and you think theta equals 0 and you go through pi over 2, pi, 3 pi over 2, we need this to vary continuously. We need it actually to be a smooth function, at least differentiable, for all the stuff to make sense. And the problem is you're inexorably forced to get to values that are very, very, very close to 2 pi as you go up to here, and then suddenly, boom, there's going to be a discontinuity and they shift back to 0. So there's no continuous way to make this. And of course, if you actually look at this formula, this doesn't even work when x equals 0, so that doesn't even work here. But you can make theta well-defined, if you are a little more careful, on everything but one chosen ray. You could use this, you could use this, you could use this, you could use this. You could even make it wiggly going out, as long as you have some sort of what's called a branch cut to avoid that fact of going back down, basically kind of off a cliff. The height, if you think of this as like a height function. It's like a spiral staircase going up, 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 and then bam, suddenly down. Not a very good spiral staircase. So we often refer to this form in 2 dimensions as d theta, remembering that that's not really an exact form. Okay, but so I wanted to mention that. So this form is really important in all dimensions. When you look at this very simple space, Rn minus the origin, and you have a closed but not exact form. So here's some notes, stuff that we're not going to do as problems or prove. Okay, so the claim is that if p is not equal to 0, which we know is always special, or n, which is the dimension of the space we're in, it actually is true that every closed p form on Rn is exact. Okay, so it was important that this was actually a top dimensional form. I'm sorry, I shouldn't, yeah, n minus 1, there we go. It wasn't a top dimensional form, it was an n minus 1 dimensional form. Oops. But that's the only place. So at the top, almost at the top. I just said that completely wrong. So the interesting stuff's happening with n minus 1 forms and 0 forms here on Rn minus the origin. Okay, and even in degree here, n minus 1, I should have said that. Alpha, it turns out alpha is essentially the only example. So this is very much like what was going on in those topology handouts, that once you've found this example, then you can multiply that by any real number, and that's going to be yet another form that's closed but not exact. But the claim is that if I take any other closed form, and this is again an n minus 1, I just bobbled that, then this guy is going to be of the form some multiple of that alpha plus delta. And in fact, you can even figure out what multiple it is by taking your gamma and integrating it over the unit n minus 1 sphere, because that's going to, you can then compare to what alpha does when you integrate it. This is exactly the generalization of some of the key examples on those topology handouts. Those really were special examples of this phenomenon. Okay, so that's what's going on with Rn minus the origin. P equals 0 is always special, and then there's this special n minus 1 form, and that's really the only interesting example. That's not something that I'm prepared to prove with the level that I'm pitching this at. Okay, good place to stop, but we're going to look at one more example that's kind of, again, generalizing the topology handouts.